Hello, my name is Matt Wright, and here I am coming to you live to talk to you about how you might find the potential of a charge near a conductor. Now, this is one of my favorite all time. I love this. I can't believe how wonderful this is thing in science. We know that the Laplacian of the electric potential is equal to minus the charge density over epsilon naught. And if I have a grounded conducting plane, right? So it's grounded, so there's a wire connected to it. It goes to ground. I can determine the potential near that. Well, so first off, if I know that it's a grounded conducting plane, and let's say I call this z equals 0, I know that the potential, if this is actually inside the conductor, the potential is going to be equal to 0 on that surface. And the reason is that it's grounded, right? So if we hook this up to ground, we have voltage equal to 0. Now, if we take a charge and put it here, interesting things can happen. All right, so if we put a positive charge there, then in all the space near this positive charge, the charge density is going to be 0. This, in fact, gives me a somewhat complex differential equation, which is just the Laplacian. Now, if I find a solution that works in this differential equation and matches my boundary conditions, then it's a valid solution, no matter how I came up with it. What are my boundary conditions? Well, at v equal to 0, v at z equal to 0 has to be 0. And then if I go infinitely far away from all of this, and I make z go to infinity, I would expect that the potential out there is going to be 0 as well, right? So if I go infinitely far away from all of this, from that charge, the only thing that's technically not neutral in this problem, I would expect that the potential would go to 0, right? If I looked at the charge from Mars, we really wouldn't see anything because it's so far away, right? 1 over r dependence. So those are my boundary conditions, right? This part is the part that just blows my mind. No matter how you come up with a solution, if it is a solution and it fits my boundary conditions, it is a valid approach to solving that differential equation. So imagine if I put on my witch's hat and I had my broom and my cauldron and I flew around it and I threw Newt's eyeballs into the cauldron of green goo and I conjured up a solution and I used it in that differential equation and it worked and it matched that boundary condition and the other boundary condition at infinity, then in fact that is a valid method of solving that differential equation. I mean, that kind of makes me speechless, right? Because that's not how we think of when we think of math. We think of like, all right, you gotta like solve this algebraic thing and you go like one step at a time all the way to the bottom. And here I'm saying, like, No, conjure up a solution, test to see if it's valid. All right, well, we already know that the solution to this differential equation is, if I have a single point charge, is going to be 1 over 4 pi epsilon naught, right? Q over script r. And we already know that this is a solution to that differential equation, right? We've done that to death already now. That was what chapter 2 was about, right? So if I take some point here, point P, right? If this is my origin, this is some distance z prime away, right? Maybe we call it d, right? And then this is at some value x, y, z, right? So, and here, of course, we'll just make x prime and y prime equal to 0. So, this is just right above the origin, and this is at some arbitrary point far away. And of course, script r is that distance, right? And so at first look, we're like, okay, that can tell me what the potential is due to this point charge here, but does it match the boundary conditions? Well, would I expect it to be 0 here if I put my point P there? And the answer would be no, because you'd be a distance d away from the charge, and your potential would be 1 over 4 pi epsilon naught q over d. So our initial assumption for what we would put in here doesn't work. It's time for our spooky magic. I am going to conjure up a mythical charge, and I'm going to put it right here. Doesn't exist. Hint, I made that shit up. Right? I conjured it up. And I happen to put it a distance of, I happen to put it at a location of minus d. Right? And I gave it, if the charge here was q, of course, it's a negative charge, so I'm going to give it minus q. And I'm going to rewrite this as, I'm going to add a term, because we have this mythical charge here, right? And I have my second script r, let's call it script r star. And it's going to be 1 over 4 pi epsilon naught q over script r star. So now the question is, does this fit this differential equation? Well, of course it does, because this differential equation is going to work for a point charge, right? Again, chapter 2. So it works, but does it match our boundary conditions? Let's think about that. Well, I know that if I go infinitely far away from this, infinitely far away from D in any direction, I should get 0 for my potential. So let's think about that. Well, if I take this point P and I move it out to, say, that point, and I write down what script r is, it's not going to matter. Both of these distances are going to be infinite. So if I move my point P over here, which is infinitely far away, that's going to be infinity. That's going to be infinity. I put infinity into each of these equations. 1 over infinity is 0. It matches. Cool. So I match my infinite boundary condition. But let's think about what happens at the middle. Right? What happens at that location? Okay. So let's write it out. I'm going to bring it over here. So we're going to have q over 4 pi epsilon naught and then we're going to write out what our script R is. So the first script R, if say I pick a point here, this is going to be at, Z prime is going to be at Z, right? But here, Z is going to be equal to 0. You might have an X and a Y. So when I write out what my script R is, it's going to be X squared plus Y squared plus 0 minus Z prime squared, right? Remember that script R has an X minus X prime, a Y minus Y prime, and a Z minus Z prime, right? Here, X prime and Y prime are at the origin, right? They're right above the origin. So for this one, I can just reduce that down to X squared, right? Because X minus X prime is X when X prime is 0. The same is going to be true for the Y. But now, if I move this point here to this surface, the Z is going to be 0 because it's going to be sitting on that surface, right? So, but the Z prime isn't 0 because that's a certain distance away. And okay, so then I have this term here, the script R prime, and that's going to be that script R star at that point P. And so that is going to be minus 1 over the square root of, again, X squared, Y squared, plus a minus times a minus Z prime squared. Well, it doesn't matter because I'm going to square that. And the squared is going to make that positive. It's going to make that positive. So I'm left with V is equal to Q over 4 pi epsilon naught 1 over the square root of X squared plus Y squared plus Z prime squared plus, it's minus 1 over the square root of X squared plus Y squared plus Z prime squared. Or I could write D for Z prime, right? Because I'm a certain distance D away, right? It's the location that this charge is. So what's going to happen here? Well, this term's only going to be positive, and that term's only going to be positive because of the squares. So, and well, the terms are the same. So if I subtract them, I'm going to get 0. So whenever Z equals 0, this term, for no matter what value of X or Y I have, is going to be 0. So it matches the boundary conditions. So this is a solution. Let that sink in for a moment. Okay, now that we've proved it, let's go back and think about it. Because the thinking here is almost important than the proof. Almost more important than the proof. So, I have a conducting plane. V is equal to 0. Cool? I bring a charge up to it. Now, inside the charge, there is an image charge. Does it exist? No, it does not exist. It's as if it exists. So if I'm here at this point, I feel this charge and I feel that charge. But that doesn't exist. So what gives? Well, I know my potential. Let me write it out for this point. You're going to have, so this is D, right? And so this is D. So this is at X, Y, Z. So So your potential here is going to be Q over 4 pi epsilon naught 1 over the square root of x squared plus y squared plus z minus d squared minus 1 over the square root of x squared plus y squared plus z plus d squared. Right? When you're, this one has a, the z goes an extra distance because the script r here is small and this one is larger. So here you have z minus d, here you have z plus d. Right? So if you're here, right here at this point, here you would get this distance would be 0 because you'd be right above that. But here your distance would be large. Right? And if they're exactly in the center, we have the situation where they cancel. That's what the potential is here. But the potential here is 0 because this is inside a conductor that's grounded. Inside a conductor that's grounded. So, what to do? Well, how would I determine what the electric field is on this particular, at this particular point? Well, I know if V is equal to 0, E, and it's in a conductor, right? It's in a conductor, so I know that the E field inside the conductor is 0, right? You could say, well, wait a minute. Isn't E just the gradient of E? Well, sure, and if V is equal to 0, and you take the gradient of 0, you definitely get 0. So, this thing is really an image charge that doesn't exist, that's floating in space, that we conjured up, which matched the boundary conditions, and is a solution to the Laplace's equation. So it works. Of course, that's not fair. So what's going on? Well, as I bring the positive charge close to the conducting surface, this positive charge is going to attract negative charges. So the negative charges are going to swarm to this surface. And they're going to swarm to the surface and distribute themselves in such a way as to yield a potential that looks like that. So what really happens is there are charges there, a surface charge density on this surface, physical charges, negative charges, which have moved to the surface, right? And they've moved into the surface in such a way that if you add up their effect, it's as if, exactly as if, there was one single image charge that was a distance d away from the surface of the conductor. That is like insanely mind-blowing, right? We conjured up a solution, it works. Now, we made up some crazy model, right? And now we're finding out that like stuff's happening to like add up in such a way to prove our model right. Oh, that's confusing. How do we find what that charge, that physical charge is on that surface? Well, we know how the boundary conditions for the potential must be. We know that if I go from this side of the boundary to that side of the boundary, the potential, so we call this region 1 and region 2, the potential 1 has to equal potential 2 because we know that the potential is continuous. I always get this minus sign wrong. I'm going to take a quick look. Oh, this minus sign kills me. Where are you, minus sign? Oh, little stinker. Okay, so we know that on a boundary with one of these sides equal to 0 on the conductor, we know that the electric field, right, is equal to sigma over epsilon naught n hat. So how do we know that? Well, we take a little Gaussian cylinder here, right, along that thing here, and you know that this side's going to be EA, right? And any field's going to come out of these charges, and it'll be perpendicular to the area pointing out. So the, hello, it's Professor Panettiere. Hi, Professor Panettiere. Hi. So we know that the electric field is going to be pointing out of the negative charges, and the area is going to be pointing perpendicular here. So that's going to give us 0 right here. And on this side here, on that side of the boundary, I'm inside the conductor. So E is equal to 0, right? So that tells me that the electric field right here is going to be equal to the charge enclosed, right? So let's see, EA equals charge enclosed over epsilon naught. You divide by A, you get 1 over epsilon naught, Q over A, but that is in fact just sigma. And of course the E points along the direction of the surface. So if I look at this and I think about this in terms of what this would be in terms of the potential, I am going to look at the gradient of V in the direction of the surface. And here I have this surface to be the Z direction. So I'm going to take the partial of V with respect to Z, and that is going to give me sigma over epsilon naught. Of course, I got to put in my boundary condition of Z prime equals 0, right? Because I'm going to be taking the potential right at where the boundary is, so right here. So what I can do is just take this equation and plug it in here, and I can find the value for sigma. Right? And then we can just use the potential in any old way that we normally would. Right? We can find the electric field that this feels due to that image charge over there. So we could say that the force that this thing is going to feel, the force it's going to feel is equal to minus Q squared over 4 pi epsilon naught times this distance, the distance away. So it's going to be 1 over 2d squared, right? And it's going to be moving in the k hat direction. So how did I get to that force? Well, remember when we find the force, right, we treat it like that charge isn't there. And we figure out what the potential, what the field effect is from all of the charges that are there in its place. So if we have a 2-charge system, say the real charge and the image charge, we neglect the real charge. We use the image charge to determine what the electric field is at this spot. I multiply it by the charge there, right, because it's QE, right, that's the force. So I'm basically taking the electric field from just the image charge alone. I'm putting it in here. I'm taking my Q, which is the Q here, and I am going to just put in what the electric field is due to this image charge, right? And it's 2d away, right? It's along the z direction, and I can actually figure out what the force is. And so here's an amazing thing. As you get closer and closer to the conductor, you get more and more force, and it's attractive. So this charge is actually attracted to this neutral conductor, which of course has redistributed its charges so that its negative charges are on the surface. Whew! So in class, we're going to look at determining what the energy is, right? We have to think about it when we integrate E in all space, what that means for the energy.